Uh, Hello, my dear students. This is the part third of lecture 4, major on semiring with course code MMTC 202. So, in this lecture, we give the necessary and sufficient condition for a semiring to be a major. So we have a following theorem. Let S be a semiring. Let S be a semiring, and mu is a set function from S to 0 to infinity. Then mu is a major on S if and only if it satisfies the following properties. Property 1 is mu of phi should be equal to 0. Mu of phi equal to 0. And second property is if A belongs to the semiring S and A1, A2 up to AN, they are also the numbers of S, such that this union is subset of union I runs from 1 to N, AI is subset of A. Union is subset of A, and these AIs, they are also pairwise disjoint. They are pairwise disjoint. Then mu, this summation I runs from 1 to N, mu of AI is less or equal to mu of A. And third property is if A is in S, and AN is a disjoint, sequence in S, is a disjoint sequence in S, not a disjoint, it's any sequence, it's not disjoint, is any sequence in S, with A subset of union AN runs from 1 to infinity, runs from 1 to infinity, then mu of A is less or equal to summation runs from 1 to infinity mu of AN. This property is called sigma subadditive. So that is mu is sigma subadditive. So in this theorem we show that a set function mu is a major if and only if this function mu satisfies these three properties. So we first assume that mu is a major, and we prove that a major has these three properties. So first assume that mu is a major. Prove. Assume that mu is a major on S. Our first property, that mu of phi is 0, it's trivial. Mu of phi is 0, it's by definition of mu. By definition of mu. Mu is a measure, so mu of phi is equal to 0. Now going to second property. So let A belongs to S, A1, A2, there are n sets in S such that union I runs from 1 to n, AI subset of A. AI subset of A. We need to show that summation I runs from 1 to n mu of AI is less or equal to mu of A. Is less or equal to mu of A. That's the second property that we have to prove. But so here this the union is subset of A. So we have the difference A minus union I runs from 1 to n AI. So it's already done that. The difference can be written as the finite disjoint union of members of S, where BI's, they are the members of S and they are pairwise disjoint. Oh, this is already done. Huh? The difference of these two sets, A minus union I runs from 1 to AI, is equal to B1 union B2 union Bm, where these Bi's, they are the members of S, and these sets are also pairwise disjoint. So now we construct a finite class of sets. Now let's define C1 is equal to A1, C2 is equal to A2, up to Cn is equal to An. Then define Cn plus 1 is equal to B1 and Cn plus m is equal to Bm. So we have now these n plus m sets. They are pairwise disjoint. These are Cn plus 1 up to Cn plus m, they are pairwise disjoint. And now these C1, C2, they are A1, A2, An. They are also disjoint from these B's, because this A minus union I runs from 1 to n AI is disjoint from the union I runs from 1 to n union AI. So then this these sets, these n sets, then Ci intersection Cj is phi for all 1 less or equal to I comma j less or equal to n plus m with I not equal to j, with I not equal to j. This is so now we have this A, it's equal to union Ci I runs from 1 to n plus n. You can easily verify it. This unit is equal to that. That implies mu of A is equal to mu of union I runs from 1 to n plus m Ci. Since mu is a measure, so that means therefore this mu is finite additive. Every measure is finite additive. So this mu is finite additive. So that means mu of finite union is equal to sum of the mu's, where the condition is that this union should be the member of S. But here it is a member of S because this union is equal to A and A is a member of S. So therefore this is equal to summation I runs from 1 to n plus m mu of Ci. And that's equal to summation I runs from 1 to n mu of Ci plus summation I runs from n plus 1 to n plus m mu of Ci. And for I runs from 1 to n, Ci is equal to Ai. So it's equal to summation I runs from 1 to n mu of Ai plus that summation I runs from n plus 1 to n plus m. It's n plus 1 to n plus m. This is mu of Ci. Okay. Now this one, this sum is greater or equal to first term. It's greater or equal to summation I runs from 1 to n mu of Ai. So that's the part second. This proves part second. Mu of A is greater or equal to summation I runs from 1 to n mu of Ai. Now we prove the third part of this result. Third part means we have to prove that this mu is sigma sub additive. So for third part we choose let A is a member of S and An it's be a sequence in S. It's a sequence in S such that A is subset of union A and n runs from 1 to infinity. So we show that this is mu of A is less or equal to. We show that mu of A is less or equal to summation n runs from 1 to infinity mu of A n. This we need to show. We express this union as a disjoint union of members of S by defining the following. So let's define the following sets. Define B1 is equal to A1. It's already explained. B2 is equal to A2 minus A1, and in general Bn plus 1 is equal to An plus 1 minus the union of the sets A1, A2, An. I runs from 1 to n Ai. So then Bn's are disjoint. That's trigger. And one more thing is that union An runs from 1 to infinity is same as union Bn runs from 1 to infinity. That's important. The union is same, but now the sets on the sets in the union on the right hand side, they are pairwise disjoint. So and one more thing is that, and this An is bigger than Bn, so that means Bn is subset of An. That's also Bn is subset of An. Now again, since Bn is equal to An minus union I runs from 1 to n minus 1 Ai by our construction. So it's a difference of An and the union of n minus sets of S. So therefore this difference can be written as finite disjoint union of members of S. So let us write it as union I runs from 1 to kn, then Cin. So this n is fixed here for Bn. So if that means this B1 is equal to union I runs from 1 to K1 Ci1. B2 is equal to union I runs from 1 to K2 Ci2, and so on. In general, Bn is equal to I runs from 1 to K and Cin. Well, what are these Ci's? Cins? Cin, they belong to S and they are also pairwise disjoint for I not equal to J. Okay. So then this Bn it's actually subset of. So then since Bn is subset of An, but here Bn is equal to this union, so it means that union I runs from 1 to Kn Cin is subset of An as Bn is subset of An. Bn is subset of An. So let's apply the mu on both sides. Mu is a major and therefore mu is monotone. That means mu of union I runs from 1 to Kn Cin is less or equal to mu of An. Alright. So now this union, it's a disjoint union, finite disjoint union, and they are the members of S. This Bn this union Cin I runs from 1 to Kn is subset of An. So this means that each if the union is subset, so that means each set is a subset of An. So major of each set is less or equal to An. But so this implies let's apply the finite additive property of this mu. This means summation I runs from 1 to Kn mu of Cin, it's less or equal to mu of. So this one is equal to sum. Now for n equal to 1, we can set this K1 is equal to 1 and C11 is equal to A1. So we can set that notation here for n equal to 1. For n equal to 1, we can set K1 is equal to 1, C11, it's now C1 K1 actually. We can set this as A1. So there is no loss of generality. So we can assume this assumption. We don't lose anything by assuming this. It is for n equal to 1, we can assume that K1 is equal to 1, C11 is equal to A1. Okay. So we can also rearrange the sets so that this we must have this assumption here. K1 is equal to 1, C11 is equal to A1. Okay. Now we take A. Now A is equal to A intersection union A and n runs from 1 to infinity. This is because this A is a subset of the union as A is subset of union and runs from 1 to infinity A, and therefore the intersection of these two sets is the smaller set, that's A, and it is equal to A intersection union n runs from 1 to infinity B, and because union A is same as union Bn. Okay, yeah. And that's equal to union n runs from 1 to infinity by distributive law of intersection over unions. It's the union of these sets Bn intersection A. Now what's Bn? this is equal to sum A. Union n runs from 1 to infinity, and Bn is Bn is I runs from 1 to Kn. This is Cin intersection A. Okay. Yes, that's good. So this is A. This is your A. So this implies that mu of A must be equal to mu of the double union, because it's A actually. Mu of A is equal to mu of the double union. N runs from 1 to infinity, summation I runs from 1 to Kn. This is Cin intersection A. Okay. And here, since mu is a major, therefore mu is a sigma additive. If we have any countable disjoint union, then mu of the disjoint union will be equal to sum of the mu's. But the condition is that this union should be the member of S. And here it's a member of S because this union is equal to A. So I can apply the sigma additive property of a major. It's equal. So here is double union. So this should be here now double sum. Kn. And this is mu of Cin intersection A. And this one this is less or equal to this one because mu is a monotone. Cin intersection A is subset of Cin. So it's less or equal to double summation n runs from 1 to infinity summation I runs from 1 to n mu of Cin, because Cin intersection A is subset of Cin. So this, and there is no harm by taking mu of Cin. The requirement is that this should be in the domain of mu, and it is in the domain of mu because it's a member of semiring. So now what's this this sum? It's a summation I want to Kn. This is already done. It's less or equal to mu of An. It's already done. This sum is less or equal to mu of An. It's less or equal to summation n runs from 1 to infinity mu of A. So that proves this result. It's the property third. Mu of A should be less or equal to summation n runs from 1 to infinity mu of An, where this A is subset of union An, and A and the sequence An they are taken from the semiring S. So that proves the one way. Now we prove its converse. So conversely, we assume that the set function mu has these three properties. Conversely, assume that mu from S to 0 to infinity has the stated properties, has the properties stated in the theorem, has the properties stated above. Stated above means in the theorem there are those three properties. Mu of phi is equal to 0 if A belongs to S, A1, A2 up to An. They are also the members of S such that this union I runs from 1 to n is subset of A. Then summation I runs from 1 to n mu of AI is less or equal to mu of A. And the third property is sigma sub additive, means if A belongs to S and An is the sequence in S such that A is subset of union, then mu of A is less or equal to summation n runs from 1 to infinity mu of A. So these three properties we have. We prove that mu is a major. We prove that mu is a measure on S. So the first property, mu of phi is 0. Mu of phi. So that's here, it's by 1. By 1. Already, that's already there. Now next, we need to show that mu is a sigma additive. So to prove mu is sigma additive, we use the property second and property third. So second property, mu is sigma additive. So for this sigma additive property, we take a disjoint sequence, let an be a disjoint sequence in S such that the union A and n runs from 1 to infinity. Let's denote this union by A, and it's a member of S. Now by property third, it's given that whenever an is a sequence in S such that this A is subset of union A and n runs from 1 to infinity, then mu of A is less or equal to summation n runs from 1 to infinity mu of an. So here the set A is this union, and the union is they are both sets because they are equal. So we can apply this property here. The requirement is that A should be subset of the union. Here this A is equal to the union, so it's also subsets. So by property third, what's this mu of A is less or equal to summation n runs from 1 to infinity mu of A. Let's write it as a star. Now we prove the reverse. Actually, we have to prove that mu of union is equal to summation n runs from 1 to infinity mu of an. But here, what we have proved that mu of union, because he is the union, it's less or equal to summation n runs from 1 to infinity mu of an. Now we prove reverse inequality. So to prove a reverse inequality, so let n be any natural number greater or equal to 1, then this union I runs from 1 to n, it is subset of the union A and n runs from 1 to infinity. That's trivial, and this is equal to A. So is that clear? This is the finite union. It is subset of the commutable union, and that commutable union is equal to A. Now let's apply property second. That's Q. By property second, by property second, we have this summation mu of I runs from 1 to infinity is less or equal to mu of A. This is true for all n greater or equal to 1. So letting n approaching to infinity, we get summation n runs from 1 to infinity mu of an is less or equal to mu of A. Let's write this as double star. By combining star and double star, we get mu of A is equal to summation mu of an runs from 1 to infinity. This A is the union an. So mu of union an is equal to summation n runs from 1 to infinity mu of an. So therefore mu is a sigma additive. So hence mu is a measure. That proves this theorem completely. So finally, in this section, we introduce the finitely additive measure. So now we introduce finitely additive measure. So what do we mean by finitely additive measure? that S be as semiring on set X, then a function mu from S to 0 to infinity is said to be a finitely additive measure. It is said to be a finitely additive measure if first property mu of phi is 0 and second property if we have a finitely many disjoint sets, if they are in S, but they are only finitely many, not countably infinite, such that their union is also in S, such that union AI runs from 1 to n is also in S. Then mu of that finite union, that's why it's called finitely additive, finite union. In case of major, it's countably infinite. That's why at that time this property is called sigma additive, because at that time the union is countable union here, but here it's a finite union. So it's mu of finite union, that's equal to summation I runs from 1 to n mu of ai. Now, as we have already proved that if mu is a measure, then mu is monotone function. And also we have proved that every measure is finitely additive. In other words, every measure is finitely additive measure. But the converse is not true in general. And that we have proved the property for measure, that this measure is always monotone. Here we prove that finitely additive measure is also a monotone. So that's an exercise for you. So the steps are similar. That mu from S to 0 to infinity be a finitely additive measure. Then for any sets in S such that A subscript B, this should imply